Okay, so this is our lesson 5.3a. We are going to cover inverse functions and relations for 2 days. And this is kind of our first real, maybe challenging new material of this particular test section. So here's the essential standard. I understand the analytical graphical relationship between a relation or a function and its inverse. I can identify a function. I can identify if a function has an inverse function by analyzing its graph. So we'll learn how to test the graph. And I can find the inverse function both analytically and graphically. Okay. All right. So inverse relations. So remember, we can have relations between x and y, and they can be a function. If you recall, a definition of a function is for every single input, I only have one output. So you can test a graph to see if it has a a vertical line test. That means it can only pass through one point. Um, but at any rate, inverse relations will exist if all points A and B in one relation map, so a table of data of X and Y data, will then get flipped to BA. Okay, so what was my output for Y, or my output for the A value, becomes my input. So they get swapped in another relation. Now, whether or not they're functions or not depends on if they meet the function rules. Okay, if an inverse relation is expressed as an equation, okay, so we can look at it as data points or we can look at it as an equation. Its inverse relation can be found by interchanging the independent and dependent variables. Typically, the independent variable is the x-axis and the y is the dependent variable. So you can find the inverse relation by taking the x, making it a y, taking the y, making it an x, and then you have a inverse relation. Now, again, whether or not it's a function, it has to meet the function rules, one output for every single individual input. All right, because of this switching of points, the domain and range also switch. So what used to be my domain, so what used to be my restriction on my X values now becomes my restriction on my Y values, and vice versa. Okay, so let's look at some data real quick. So we have this relation on the left that says y equals x squared minus 4. I have some data points in this table. I see that, let's take the first data point. I see -3 is my input. My output is a +5. And if I go look at my inverse relation, I have the input 5 gives me an output of -3. And so they are switched between the two. I can look at another data point, such as 0, we'll say -4. And over here, I find that my input -4 gives me an output of 0. So they're completely switched. I can find those on the graph as well. So let's take, for example, my first one, which would have given me -3 for my X value and 5 for my Y value. And I can go look at where it is on the graph that is graphed in green. So I would look at my 5, +5, 1, 2, 3, 4, 5, and I would see that it's at -3. Okay. Let me see what else I want to say before I go. Okay, let's continue on. So let's look at the equations right here. So here is my equation for this relation. So y equals x squared minus 4. Just so happens that that is also a function. It is a relationship between those two x and y variables. But if you see that I can draw um, uh, it meets the vertical line test, and you can tell by also looking at the data table, there's only one output for every single input. Okay, then I can create a actual equation for this inverse relation. And all I did was switch the x and y's. You'll see that I have x now in place of y and y in place of x, and then you can rearrange and solve for y, and there's your inverse relation. does not meet the vertical line test, so it is not a function. You can see that I cross through more than one point. That means there's more than one output for a particular input. All right, so let's talk about what this looks graphically. We've already looked at the graph a little bit. Graphically, the inverse relations are reflections in the line y equals x. So we've dealt with reflections in the past. The reflections we've done in the past were on a x-axis, y-axis, or we had, well, never mind, that was symmetry, sorry, x-axis or y-axis. So let's look at the reflection here. So I'm going to take and first point out that here's y equals x. So now these graphs are reflection across that line, okay? That is y equals x is an equation for a line. It has a 0 y intercept and a slope of 1. And so that dotted red line is actually y equals x. Now let's look at where this reflection is. So let's focus on this portion of the graph. And you'll notice that on the green, this is the reflection across that y equals x line, okay? And then if I were to look at this portion of the graph, that is a reflection across that y equals x line, and that is a reflection across that, okay? So one more thing we got to go talk about is what does my notation look like? And so f to the -1 x does not mean f to the -1. In fact, it's not to be said that way. It is the inverse function of f. So if I have f of x and I find the inverse function, that -1 is not to the -1 power. It is called an inverse function, okay? Now, like what I showed you up here, this original relation, which is shown in blue, is a function. I can draw a single line through a vertical, it meets the vertical line test, but its inverse relation is not. So how do we graphically determine if a function has an inverse function? It has to meet a horizontal line test. So horizontal lines, when they're reflected across that y equals x line, becomes a vertical line. So if there is a horizontal line that crosses the function in more than one point, the original function, then there is no inverse function. So here, I see on this graph, this is my horizontal line test. It only crosses the original function one time. Therefore, that particular function has a inverse function. So let's do some examples. So here's example A. Example A, graphically, I can draw a line and I see that I can cross that function more than once. So my horizontal line shows that I have crossed that function more than once. So that means that the inverse function, that I will not pass the vertical line test, because horizontal lines become vertical lines on inverse functions. So does this have an inverse function? No. And the reason why is because it did not pass my horizontal line test. So if I look at B, I can see that if I draw it properly, I can actually go right through that area that's horizontal on the original function. I have infinite number of times that it crosses the original function. So if I were to draw that graph's inverse, it will not be a true function. It's just a relation because it failed my horizontal line test. Why don't you try one yourself? Welcome back. No matter where I draw this line, it will only cross this graph in one location. So that means it passed the horizontal line test, okay? So it has an inverse function. All right. Graphically, inverse functions are reflections, we've said this before, in the y equals x line. Okay, so here is the y equals x line. It's linear with an intercept of 0, 0. It has a slope of 1. So if I take a quick look at what does this mean? Here is a point on my original function of -1, 2. And so if I were to go and graph that point and switch the x and y values, I find that sure enough, at 2, -1, there is my data point, and that is a reflection across that y equals x line. Okay, all right. Now we're going to have to practice this, but because these points flip-flop, all right, between the x and y, whatever the domain was of my original becomes the range of my inverse, and vice versa. So the domain and range will also flip-flop. So let's figure out how to determine an inverse of a function graphically. Okay, so I have been given in a graph of f of x. I have been asked to find its inverse function graphically. So how do we do that? Well, this function in A is a piecewise function, and it only has 2 line segments. So we are going to take a look at each individual line segment. So I have the first data point, and it has a coordinate of -4, 5. And so I have to go graph its inverse function. Where is that point on its inverse function? Well, that would be at 5, -4. So x value of 5, y value of -4. And so here is where that point would be located on its inverse function. We are picking convenient points, okay? So at the end of line segments would be a really good spot. So this particular point that I just drew is at an end of that line segment. Its x value is 0, its y value is 3. And now I need to switch my x and y values and graph that data point on its inverse function. So that would be at x of 3, y of 0. So that would be right here. Now let's go ahead and draw that portion of the line segment of the inverse function. So there it is. All right, now we have one more data point that we should do, and we'll use blue. And at that data point, I have a value of +1, -1. And so I'm going to switch my x and y values, and I get -1, +1. And so that would be at this location here. So now we will draw that section of this graph. Okay. Try that one more time. Okay, there is my, I've completed it. Okay, I've done each segment, and notice that it is a reflection across that y equals x line. And so here is that portion of it, here is its reflection, and here is that portion of it, and here is its reflection. Okay, all right. All right, let's continue on. Number B, or letter B. We need to find some convenient points. Let's work with this line segment first. That line, that data point is -2, +4. So if I want to find its inverse, I got to flip my x and y. So I go to 4 and -2. Okay, so there's where that point is located. Let's find another point. There's another convenient point, and that point is -1, 1. And so now I have to flip my x and y. So I go to +1x and -1 in the y direction. There is my first portion of that line segment. And then I'm going to pick my last data point. I'll pick this one at the end. Again, pick them strategically. That is 5, -1. And now I need to go to -1x value, +5y value. And then we can draw that line segment. All right, so if we draw that line, it looks like this. And we can see that it is indeed a reflection across my y equals x line. Okay, so this portion here is reflected on this portion here. And this portion here, which has this little dog leg, is this portion here. Okay, so that's how we find that graphically. Okay, and we can also, again, see that it is reflected across my y equals, I'm going to make this a little bit clearer. There we go. All right. My y equals x line. All right. Why don't you try one yourself? Pause the video and welcome back. All right. So we got to find some points that are convenient. And so let's see. Convenient points. I think this is a convenient point right here. So that point is 6 and 3, x value 6, y value of 3. So I need to have a x value of 3 and a y value of 6. It'll be right here. Okay, next point. This is a convenient point that has an x value of 4, y value of -1. So I need a -1, +4. That's over here. So there's a portion of that graph. All right, and then we have to pick one more convenient point. We can use this one if we wanted to. Notice this is -6 and -6. And so we get the same point. That was convenient. Why did we get the same point? Well, because it's actually on that y equals x line, which is where my reflection was. So that is the reflection of that graph. All right. So another key feature about inverse functions, the domain of f is this set of x values that are highlighted in blue, becomes the range of the inverse function. Okay, so domain again is my inputs. Those values become my outputs of my inverse function. And in the same fashion, my range of f becomes my domain of my inverse of f. So those become, these are my outputs. Those outputs become my inputs. Okay, so if we look at this equation, or this f of x is equal to x plus 4. So if I have an input of 3, I get an output of 7. And my inverse function takes that input of 7 and gets an output of 3. So my inverse function undoes essentially what my original function did to my x value. So this leads us to this next key concept. Two functions f and g are inverse function if and only if f of g of x equals x for every x in the domain of g of x, and g of f of x equals x for every x in the domain of f of x. So what does that mean? We're going to input x into g of x, which is the inverse of f. And what are we going to get as my output? I'm going to undo what I originally did. And in the same fashion, I have to, if I put x into f of x, and then take g of x of that, I'm going to undo it. I will get x back. So if I input x into one, essentially the inverse function undoes what we originally did. Okay, so here's what we are going to do. We are going to test these functions to determine if they are inverse functions. And how do we test it? We have to apply this key concept. Okay, so f of x equals 2x plus 3. G of x equals x plus 3 over 2. We are asked to find f of g of x, g of f of x, and then answer the question, are they inverse functions? Okay, so you know how to do that. What is f of g of x? Well, the function g of x becomes my input for x. So I need to put in g of x into this x value. So what does that look like? That is going to look like 2 times x plus 3 over 2 and then plus 3. I have to simplify. I get that equal to x plus 3 equals x plus 6. Okay, now what is g of f of x? So now I'm going to take my f of x and input it into the x within g. And so what does that look like? That is equal to 2x plus 3 all over 2. We will simplify that, and I get 2x plus 6 over 2 equals x plus 3. All right, I've answered the first part. Now the second part of the question is, are the functions f and g inverse functions? And the answer is no. What was my input? My input was x. My input was x. Did I get back x? No, I got x plus 3 for one, and I got x plus 6 for the other. So the answer is no. Why don't you try one yourself? Welcome back. I got to take this g of x and put it into this x here. And what do I get? I get x minus 10 and then plus 10. I get the answer x. All right, that one checks. Let's do the next one. I get, I have to input f of x into this x, so I get x plus 10 and then minus 10, and that equals x. This checks. So I got x back when I took f of g of x and g of f of x, so the answer is yes. C. I will take I will put 3 over negative 3 over x. Okay. I need to simplify that. I can do so by multiplying both top and bottom by the inverse. Both top and bottom by the inverse. And I will get negative x. All right, how do I get that? Negative x. Well, negative 3 cancels. This cancels, and I get negative x on top. Then the next one, g of f of x is equal to negative 3 over x. That is equal to, again, negative x. Okay, the answer is no. Don't be confused. Negative x and negative x, this looks like it might be an inverse function, but in reality, those are not, they don't undo themselves. I had an input of x, I had an input of x, I need to get an output of x. I got an output of negative x. All right, try one yourself. Welcome back. I have to input g of x into, so 2, whoops, I get 2 times 2x minus 1 plus 1. That becomes 4x minus 2 plus 1. That is equal to 4x minus 1. Now you already know that the answer is no. It's not an inverse function. G of f of x, I get 2 times 2x plus 1 minus 1 equals 4x plus 2 minus 1, and I get 4x plus 1. The answer is no. All right. I hope that makes sense. Reach out to me if you have any questions.